Okay, so welcome to the final part of looking at using definite integration to calculate exact areas. So we've got another question here. We've got a graph with a line y equals x plus 4, and we've also got a quadratic y equals minus x squared plus 8x minus 6. And the question is asking us to find the exact area of the shaded region bound by the quadratic and the straight line. Okay, and similar to part 2, this question isn't going to be solved by simply calculating or performing a single integral. We're going to have to carry out multiple steps. So the first thing that I'm going to do is I'm going to sketch out the graph, and similar to part 2, or one of the questions in part 2, I'm going to sketch out the graph, but I'm only going to include the quadratic. Okay, I'm going to label our points A and B. Now, if we were to integrate our quadratic using these two limits, we would find this area. Okay. Now, we can see that in the actual question, we can put this area down like this. We're missing a chunk, aren't we? Similar to the previous question we did in the previous video. This time, that chunk that we're missing is a trapezium. Outlined here. So, what we're going to do is, in a very similar fashion, we're going to calculate this area, and then what we're going to do is calculate the area of the trapezium, subtract that area from this larger area in order to find the shaded region. Now, that's not all we've got to do here. You can see that in the question, we don't know the coordinates of point A or point B. And so we need to find the x coordinates and also the y coordinates so that we can calculate this area, but also calculate the area of the trapezium. So let's start off by trying to calculate this area. The integration or the integral that we will be performing is as follows. So we'll be integrating our quadratic. We're looking at the area under that quadratic. So that's what we're going to do. Minus x squared plus 8x minus 6, and now we need to put in our limits. This is where we need to find the x coordinates of A and B. How can we do this? Well, we know that at A and B, the line and the quadratic term intersect with each other, and that means that the x coordinates at these points must be the same for these equations. So what we can do is equate the two equations together. So we've got minus x squared plus 8x minus 6. Okay. Now to solve this, I'm going to bring this over this side, so we've got a positive quadratic term to deal with. It's always easier that way. I'm going to bring the 8x over, so subtract 8x from both sides to get minus 7x. I'm going to add 6 to both sides to get 10. Okay, and that equals 0. If I factorize that now, or if you use your calculators to solve, you will find that x equals 2 or x equals 5. Okay, so by inspection we can tell that A is going to have the 2 or the x coordinate of 2, and B is going to have the x coordinate of 5. Okay, so now we can put those limits in. Perfect. There we go. Okay, and I forgot my dx. Okay, so now let's perform that integral to find this area. So minus x cubed over 3 plus 8x squared divided by the new power minus 6x. Okay, and we can simplify that middle factor to be 4x squared. Okay, that's the term in brackets. We've got 5 and 2. So minus 5 cubed over 3, add 4 times 5 squared, minus 6 times 5, all in a bracket. And then we're going to subtract the same expression, but this time substituting 2 in. So 2 cubed over 3, add 4, 3, oh, not 3, 2 squared, plus 6 times 2. Okay, and if you put that in your calculator, you'll get 27. Okay, so that's the first bit done. Now we need to move on to the second step of calculating the area of this trapezium. So, we know that the area of any trapezium is equal to the average of the lengths of the two parallel sides, so in this case this line and this line. So it's the average of those two lines, let's just call them line 1 and line 2. So the average of those two times by the perpendicular height. Here we know that the perpendicular height is 3 because it's 5 minus 2, the two x coordinates. Now, what we need to do is find the heights of the two parallel lines. Now, the way we can do that is use the fact that A and B both lie on this straight line, y equals x plus 4. We know the x coordinates for A and the x coordinates for B. And if we know what the x coordinates are, we can therefore work out the y coordinate. So at A, y equals x plus 2, x is equal to, y equals x plus 4, and x is equal to 2. So our y coordinate is 6. For B, we use the same process to find that y equals 9. So we've got the length of this line, which is going to be the coordinate of A, or the y coordinate of A, which is 6, minus the coordinate here at the base, which is 0, so that length is 6. And using the same logic, this length is also 6. So we've got the length of line 1, add the length of line 2 over 2 times 3, which equals the area of our trapezium. And that is 45 over 2. So, what have we found? We have found, firstly, the area between the limits a and b under the quadratic curve, and then we found the area of this trapezium. Now that we've got those two values, we can subtract the area of the trapezium away from the area under the curve in order to find the exact area of the shaded region. So this was 27, this was 45 over 2, so the exact area equals 27 minus 45 over 2. That equals 54 over 2 minus 45 over 2. So we've got 9 over 2, or 4.5 units squared. Okay, so I just wanted to wrap up this video and areas under curves in general by sort of talking about some of the patterns that keep cropping up with these types of questions. So with all of the questions, you've seen that we've had to find some area under a curve. So in this example, it was, if we had A and B, we were finding this area. And that was using our integration skills. So we're integrating between the limits 5 and 2, and we put our function in there. So that is always going to be the first part of these styles of questions, is carrying out some sort of integral between limits. The next thing that you're going to have to do is work out how this how the boundaries, how the additional boundaries, so it might be a line, it might be another curve, how are they cutting off the area that you've got here into something smaller like here? And what shape does that leave behind? In this case, it left a trapezium. Then you need to, using your kind of basic math skills, find the area of that shape that has been cropped off of that initial area that you've got under the curve here. So that might be a trapezium, it might be a triangle, it might be a rectangle or a square. But you need to work out or identify what shape it is and work out that area accordingly. And that is kind of as tricky as it gets. The tricky part is identifying the shape that has been produced, and then you might also have additional steps like finding the coordinates or the limits that you need to integrate between, finding where curves and lines might intersect to give you these shapes so that you can find the base and the height and these kinds of things. But that is the general idea and the kind of problem solving skills that they want you to have in the exam.